Okay, good morning. We're going to continue with momentum. Uh, we're going to talk a little bit about the law of momentum conservation. So when we say the law of momentum conservation, what we mean is that in an isolated system, and we'll discuss a little bit more about the isolated system. If you have a collision between two objects in an isolated system, and what we mean by that is just those two systems involved in the collision. You don't have any other, and there is no external force. The total momentum before the collision is equal to the total momentum after the collision. Again, remember that momentum is mass times velocity. So if you were to add up the mass times velocity of the system before the collision, it's going to equal to the mass time velocity after the collision. The total momentum is conserved. That is, if one object gain momentum, the other object is going to lose momentum. So the momentum gained by one object is equal to the momentum lost by the other object. And that is the law of momentum conservation. So again, let's just look at it another way. If you have two objects colliding, and as we have said before, Newton's law says that if you have contact, or if you have contact between two objects, then one object is going to exert a force on the other object, and then the other object is also going to exert a force on the first object. The force are going to be in opposite direction, but the magnitude is going to be the same. So when you have a collision between two objects, the force exerted by one is going to equal to the force exerted by the other. Okay, remember that forces comes in pair, but the direction of the force is going to be opposite. One is going to be in one direction, the other is going to be in the opposite direction. When you have contact between two objects, the contact time is important. So and the contact time is going to be the same. So if you multiply the force times the contact time for one object, it's going to equal to the force times the contact time for the second object. It's just that the force is going to be in the opposite direction. Remember that force times time is what we call impulse. And impulse is the same thing as momentum change. Momentum change is the mass times the change in velocity. Okay? We look at some of these questions. So we're going to move on now. We're going to look a little bit more in depth on the law of momentum conservation. And when we talk about an isolated system, it's a collection of two or more objects. It is free from external force. It's just the objects in the system that is involved. You don't have any external force being involved. So the only forces acting between the objects is the contact force between the objects, okay? So the only forces acting between the objects is a contact force between the objects. If you look at the collision of two billiard balls, so this would be an isolated system. So this is one billiard ball and this is the second. If there's a contact between them, if you look at all the forces acting on the billiard ball, you have the force of gravity, you have the normal force, and then this ball is going to contact this ball, but this ball is also going to contact that ball. Okay? So the force acting on this ball is going to be in that direction, and then the force acting on this one is going to be in that direction. I will call those the applied or the contact force. So this is an isolated system. Okay, the only forces acting between them is the contact force. All right, so so remember, when to get an acceleration, you need unbalanced force. So the only unbalanced force are the contact forces that's applying between the balls. All right, for you to get acceleration, Newton's second law, force is equal to mass times acceleration. For you to get acceleration, you need unbalanced forces. So the only unbalanced force here is the contact force that the balls apply to each other, because they're going to come in contact with each other. Okay? Um, the contact forces are the internal forces. There are no external force. And that is what we call an isolated system. You also have to assume that the frictional force is small. Okay? And if all these conditions are met, then the total system momentum is conserved. That is, the momentum before the collision is equal to the momentum after the collision. So that is the important about the law of momentum conservation. The momentum before collision is equal to the momentum after the collision. There shouldn't be any external forces. The only force that should be acting is the contact forces between the objects. And you have to assume that the frictional force is small, negligible. And again, the momentum lost by one object is equal to the momentum gained by another object. So momentum lost by one is equal to the momentum gained by the other. With the law of momentum conservation, we can use this principle, or this law, to determine pre and post collision velocities. And this is very, very important, because any situation where you have a velocity and a mass, you can determine the pre and post collision velocity. And we're going to do some examples to further explore this. When you have collisions, there are different types of collisions. And we spoke about elastic collision before. An elastic collision, remember, is when the speed before the collision is almost identical to the speed after the collision. So you talk about, with elastic collision, you talk about a large velocity, a large momentum, large impulse. In opposition to your inelastic collision, when you have an inelastic collision, the total kinetic energy is not conserved. What we mean by that is that some of the kinetic energy is transformed into non-mechanical forms of energy, such as heat and sound. So some of the energy is lost as heat and sound. Okay, when you have a collision, of course, you're going to have heat. Things going to heat up. So you might see sparks, and you're going to hear sound. So that is some of the kinetic energy is being transformed to transform into other forms of energy. All right, let's look at some examples so we can further explore this law of momentum conservation. So in a physics lab, a 0.5 kilogram cart moving rightward with a speed of 92.8 centimeters per second, and it collides with a 1.5 kilogram cart moving leftward with a speed of 21.6 centimeters per second. The two carts stick together and move as a single object after the collision. Determine the post-collision speed of the two carts. So you have two carts colliding, one moving to the right, one moving to the left, different speeds, different mass, and they collide. But they stick together and they move leftward with a certain speed. Sorry, they stick together. They didn't say what direction. You have to find out the direction. They stick together and move as a single unit after the collision. So you're going to determine the post-collision speed of the two carts. And by doing by using the law of momentum conservation, you can determine what direction it's going to be moving and what speed. So let's use the law, or let's use the law as we outlined. So let's look at the pre-collision momentum. All right, so pre-collision momentum. All right. So for all right, let's put momentum. The symbol for momentum is rho. So the pre-collision momentum for the system, the two objects in the system. So the mass times the velocity is the momentum. The object is moving rightward, so the velocity is positive. Moving rightwards, velocity is positive. So we're talking about a 0.5 mass times the velocity, which is 92.8 centimeters per second. Okay, so this is for the 0.5 kilogram cart, and then the momentum of the 1.5 kilogram cart is moving leftward though. So because it's moving leftward, it's going to have a minus sign, right? Remember, velocities moving leftward or downward is negative. So the mass is 1.5. So the sign is very important. If you don't put in the correct sign, it's going to be incorrect. So the mass, 1.5, times the velocity, which is 21.6 centimeters. And when you do the math here, okay, when you do the math, you get 46.4. So 0.5 times 92.8 is 46.4. You're going to subtract from that 1.5 times 21.6. And that is 32.4. 32.4. And that is 14. So the momentum before the collision is 14. The signs is important. The velocity will tell you what direction the objects are moving in. You have to put the signs in. Okay? The unit of momentum is mass, and the mass here is in kilograms. So it's kilograms. And the velocity is centimeters per second. So is kilogram centimeters per second. Okay, so that is pre. So post collision now. So post collision, because momentum is conserved, so the momentum pre-collision is equal to the momentum post-collision. So post-collision, let's look at what we got. The two carts stick together. So if the two carts stick together, the mass is going to be 0.5 plus 1.5. So the mass is 2. So you have a 2 kilogram mass because the mass is combined. And Okay, they stick together and they move as a single unit. So they're gonna have a velocity v. We don't know what v is, but they're gonna have a velocity v. From the law of momentum conservation, the pre-collision momentum is equal to the post-collision momentum. So we know that 2v from the law of momentum conservation is equal to 14. And when you solve for v, you get 7. It's positive 7. So what that tells you that when they collide, they're going to move to the right. Okay, they're going to move to the right with a velocity of 7 centimeters per second. Okay, pre-collision momentum is equal to post-collision momentum. All right, so let's erase that and let's move to the next problem. All right, so problem number 2, a 25-gram bullet enters a 2.35 kilogram watermelon and embeds itself in the melon. The melon is immediately set into motion with a speed of 3.82 meters per second. The bullet remains lodged inside the melon. What was the entry speed of the bullet? Okay, so you have a 25-gram bullet. It enters a watermelon, 2.35 kilogram, and embeds in the melon. The melon moves, okay, because the bullet is going to do that. The melon is immediately set into motion, and it has a speed of 3.82 meters per second. The bullet remains inside the melon. What was the entry speed of the bullet? So you approach it the same way. Momentum is conserved. So we have to assume that so the momentum is conserved. So the pre-collision momentum so the pre-collision momentum is equal to, so you have two objects in the system. So you have an isolated system with a bullet and a watermelon. Okay, so you have to calculate the momentum for the bullet, and you have to calculate the momentum for the watermelon before the collision. Okay, so before the collision, the bullet is going to have a momentum. Let's do the bullet. So the bullet is going to have a momentum which is equal to the mass times the velocity of the bullet, and that is the entry speed of the bullet. The mass of the bullet is 25 grams. So let's convert 25 grams into kilograms. So the mass of the bullet is so when you have kilograms, you have to divide it by 10 to the power 3 or 1,000. So you're going to have 1, 2. So the mass in kilograms is 0.025 kilogram. That's the bullet. That's the mass of the bullet. And then the momentum, you have to multiply the velocity of the bullet. Call it V. So the velocity of the bullet, the entry velocity, this is the speed with which the bullet is traveling, is V. And when we multiply times the mass of the bullet, we get the momentum of the bullet. We have to add that to the momentum of the watermelon. The watermelon has a mass of 2.35, but the watermelon was at rest. So when you multiply the mass of the watermelon times the speed or the velocity of the watermelon, because it is at rest, you get 0. Because anything times 0 is 0. Okay? So this is This is the pre-collision momentum. It is 0.025 times v, and v is the entry velocity or the speed of the bullet. Just say the speed of the bullet. All right. The post-collision momentum, so post-collision momentum okay, again, momentum is always mass times velocity. So the watermelon has a mass of 2.35. You have to add the mass of the bullet, because remember, the bullet now large inside the watermelon. So the masses combines. So when you had 25 grams to 2.35 kilograms, you're going to get, so that's the mass, you're going to get 2.375. So these little steps are very important, because if you miss something, you're going to get you're going to get incorrect answer. Okay, so all right, so this is the mass of the bullet and the watermelon. You're going to multiply this by the velocity of the combined bullet and watermelon, which is 3.82. 3.82. Momentum is mass times velocity. But because the bullet large inside the watermelon, the total mass is this, velocity you're given. So remember, the momentum is conserved, so the pre-collision momentum is equal to the post-collision momentum. So what we can say is 0.025 times v is equal to 2.375 times 3.82. So when you solve for v, v is equal to v is equal to so all you do, you just multiply that and you divide it by that, and it comes out to 362.9 meters per second. 362.9. So you know the speed at which the bullet was traveling. Okay? Just using the law of momentum conservation, you can calculate the speed the bullet was traveling. 362.9 meters per second. All right, so I think we understand that. So let's move to the next one. All right, so question number 3. Question number 3 states that you have again a 25-gram bullet. It enters a watermelon with a speed of it entered a watermelon with a speed of 217 meters per second. This time it exits the opposite side with a speed of 109 meters per second. If the watermelon was originally at rest, then what speed will it have as the bullet leaves its opposite side? So just imagine the scenario. watermelon at rest. You fire a gun, the bullet enters the watermelon at a certain speed. It exits the watermelon with a certain speed. So the watermelon was at rest, and it's going to be, when the bullet hit the watermelon, it's going to travel a certain distance. And you're going to calculate the speed that you're going to calculate the speed. You calculate the speed of the watermelon as the bullet leaves it. So the same approach, all right, the same approach, pre-collision. So pre-collision momentum. So let's look at the bullet. The momentum of the bullet. The momentum of the bullet. So the system consists of the bullet and the watermelon. So the momentum of the bullet is the mass of the bullet. So when we convert the mass to kilograms, we get 0.25 kilograms. And you multiply it by the speed of the bullet, which is 2.17 meters per second. You now have to add to that the momentum of the watermelon. The watermelon has a mass of 2.3 kilograms, but it was at rest. So mass times velocity, velocity is 0, so you're going to add 0. This is the momentum of the watermelon. So the pre-collision momentum is 0.025 times 217. And when you work that out, you get 5.43. So this is the pre-collision momentum. Let's do the same for the post-collision momentum now. So the post-collision momentum, again, you have two objects in the system. So you do the same approach. So the momentum of the bullet is the mass of the bullet. So the bullet mass is 0.25. After the collision, the bullet loses speed. So something have to gain speed, and the watermelon gained the speed. So the speed of the bullet is 109. So you get kilograms mass times the velocity as the bullet exits the watermelon. This is 109. Okay. You're going to add to that the momentum of the watermelon after the collision. Okay. The mass of the watermelon is 2. Remember, the bullet didn't lodge in the watermelon this time. It travels through. So the mass of the watermelon, 2.35 kilograms, times the velocity that the watermelon gained. Call that V. V. Okay? So the post-collision momentum, mass of the bullet times the velocity of the bullet after the collision, plus the momentum of the watermelon, the mass times the velocity of the watermelon. We want to calculate the velocity of the watermelon. So when we simplify that, okay, let's, so we know 0.025 times 109 plus 2.35 V. That is equal to 5.43. And forensic scientists use these conservation principles to calculate all sort of stuff. So it's difficult for you to stage crime scene unless you're a physicist. All right. So when you so you have to carry all of this over to that side. Okay. When you take this over there, it becomes negative. So you're going to get 2.35 V and when you subtract this from that, you're going to get 2.7. 2.7. So when you solve for V, V is 1.15. And that is meters per second. So you see, because the mass of the bullet is so tiny, so small, it has a much greater speed after the collision than the watermelon. The watermelon only travels 1.15 meters per second. Okay? So the law of momentum conservation, the pre-collision momentum is equal to the post-collision momentum. All right. Let's look at another problem. All right. So question number 4. In a physics lab, a 0.5 kilogram cart moving with a speed of 125 centimeters per second, it encounters a magnetic collision with a 1.5 kilogram cart that is initially at rest. The 0.5 kilogram cart rebounds, so it didn't stick this time. It rebounds with a speed of 45 centimeters per second in the opposite direction. So it wants you to determine the post-collision speed of the 1.5 kilogram cart. So you have two objects colliding, okay? Two carts. One is 0.5 kilogram, the other is 1.5. They're traveling, one is at rest, one is traveling at 129 centimeters per second. The smaller cart or the lighter cart bounces off and it travels in the opposite direction. Determine the post-collision speed of the bigger cart. So the same principle, but you have to have a systematic approach. So the pre-collision momentum, okay, pre-collision momentum. Let's do the momentum for this smaller cart. It has a mass of 0.5 kilograms and it has a speed of 129. Let's say that this smaller cart is traveling to the right. Okay, so it's going to have a positive velocity. So the mass is 0.5. Mass is 0.5. So the momentum is mass times velocity, which is 129. Okay, so this is the momentum for the smaller cart. Okay, the bigger cart, the 1.5 kilogram cart, is at rest. So when we had that momentum is mass times velocity. It has zero velocity, so that momentum is 0. So that is this is 64.5. So a half of 129, 64.5. So this is the pre-collision momentum. All right. When you do your post-collision momentum now, the post-collision momentum, okay, so the 0.5 kilogram cart, that's the mass, it rebounds. So if it rebounds, it was traveling to the right. If it rebounds, it's now traveling to the left. So the velocity is going to be negative. So you have to put your negative first. Okay, the mass is, okay, so let's put a 0 so we don't confuse things. So it's minus 0.5, the mass times the velocity, and the speed was 45. So 45 centimeters per second. Okay, so this is just for the smaller cart. For the bigger cart now, the bigger cart, the momentum for the bigger cart is the mass. So you're going to add to that. This is post-collision momentum. It's the mass of the bigger cart, which is 1.5, times the velocity for the bigger cart. Let's say its velocity is v. We don't know. That is what we're trying to find. That is what we're solving for. So the pre-collision momentum, which is 64.5, is equal to the post-collision momentum, which is this number here. All right. So when we let's write it out. Just write it out. So this is minus, of course, you have to put the sign, minus 5.5, sorry, minus 0.5 times 45 plus 1.5 times v. So this is a post-collision momentum. And that's equal to the pre-collision momentum, which is 64.5. So if we take this number to the other side, it becomes positive. So we're left with 1.5 v equal to 64.5 plus, this is 22.5 plus 22.5. Remember, your signs are very important when you're doing these problems. These are vector. Okay, so that is equal to, when you solve for v, so this is, sorry about that, this is equal to 87. So when you sum this, it is equal to 87. So when you solve for v, you divide your 87 by 1.5 and you get 58 centimeters per second. Okay, because we're assuming that momentum is conserved. The pre-collision momentum is equal to the post-collision momentum. We assume that momentum is conserved. All right, let's do another one. All right, so let's do this one. So this is a more realistic situation. A 3,000 kilogram truck moving rightward with a speed of 5 kilometers per hour it collides head-on with a 1,000 kilogram car moving leftward with a speed of 10 kilometers per hour. The two vehicles stick together and they move with the same velocity after the collision. Determine the post-collision velocity of the car and truck. All right, so we're going to do our same approach. So our pre-collision momentum, let's do the truck first, but you have to remember your signs. Objects moving to the right going to have positive velocity. Objects moving upward going to have positive velocity. Objects moving downward, negative velocity. Objects moving towards the left, negative velocity. So for your 3 kilogram truck, let's look at the momentum for that. Your 3 kilogram truck is moving rightward. It's moving rightward. So the mass is 3,000. And when you multiply it by the velocity, you get the momentum. So the momentum is 5. So this is the momentum for the 3,000 kilogram truck. So we're going to add to that the momentum of the 1,000 kilogram car, because this is the pre-collision momentum, but the car is moving to the left, so it's going to have a negative velocity. So you have to put that in. And then the mass of the car is 1,000 kilogram. And it's moving with a speed of 10 kilometers per hour. So you're going to multiply that by 10. That's the momentum of the car, 10. So your pre-collision momentum is equal to, so this is 15,000. And you're going to subtract from that 10,000. And you're going to be left with 5,000. So it's equal to 5,000. So your pre-collision momentum is 5,000. Pre-collision momentum is 5,000. What is your post-collision momentum? Momentum is conserved, so your post-collision momentum should be the same thing as your pre-collision momentum. So so they stick together. They stick together, okay? They stick together, so you have to combine the mass because they're now together. So the mass of the post-collision objects is 3 plus 1 is 4,000 kilograms. Okay, and they'll have a certain, they stick together and they're going to have a certain velocity. We don't know that velocity, but the velocity is going to be v. So from the law of momentum conservation, you know, pre-collision momentum is equal to post-collision momentum. So we know that your 4,000 v is equal to 5,000. So this is, okay, this is a new type of 5,000. Just, all right, so let's write it out again. So this is 5,000. So sometimes this pen has its own intention. All right, so when you solve for v, you get 5 over 4, which is 1.14, and it is kilometers per hour. So when they stick together, they're going to move, it's a positive velocity, so they're going to move rightward with a velocity of 1.14 kilometers per hour. So you can see that the truck loses momentum and the car, or the truck lose momentum. Okay, okay, and the car was moving to leftward. So you can look at that as a gain in momentum because it was moving. It now changed direction from moving leftward to rightward. So the truck lose momentum and the car gains momentum by changing its direction, moving to the opposite. Okay, so when you have a collision and the momentum is conserved, one object is going to gain momentum and the other is going to lose momentum. So let's do one more problem so we can solidify this concept. All right. All right. So let's look at this problem. Okay, so this is American football. So those of you who don't understand American football, I mean, you just have to, I mean, you know, it's just two objects. One, they're moving in the opposite direction. And, you know, one object is going to have a certain speed, the other object is going to have a certain speed, and you want to see after the collision what direction they're going to travel in and at what speed. Anyway, so this is an American football analogy. During a goal line stand, a 75 kilogram fullback moving eastward. So they're moving from from left to right. They're moving eastward. Okay, so this is a fullback. So and he's moving with a speed of 8 meters per second. And he collides head-on with a 100 kilogram lineman moving westward with a speed of 4 meters per second. So this is a real life situation in American football. So this lineman is preventing the fullback from going into the from a touchdown. Okay, so he's preventing the lineman from getting a touchdown. So they're moving in the opposite direction. The two players collide and they stick together. You know, that's what happened when they come together. They stick together and they move at the same velocity after the collision. You're going to determine the post-collision velocity of the two players. So even if you don't know anything about American football, you use the law of momentum conservation. Okay, let's look at the pre-collision momentum. So the pre-collision momentum. So pre-collision momentum. All right, so the fullback is moving eastward. He's moving to the right. So he's moving to the right. So pre-collision momentum for the fullback is the mass is moving rightward, so his velocity is positive. His mass is 75 kilogram and his velocity is 8 meters per second. This is an 8, okay? He's moving rightward or eastward, so his velocity is positive. Now he collides head-on with a lineman, so the lineman is moving in the opposite direction, westward, or moving towards the left, so therefore his velocity is negative. So you have to get his momentum. His mass is 1,000. Sorry, his mass is 100 kilograms. And when you multiply it by his velocity, which is 4 meters per second, okay, so this is the pre-collision momentum. So 75 times 8 is 600. And 4 times 100 is 400. The reason why we have the negative because of the velocity. He's moving leftward or he's moving westward. So the velocity is negative. So the pre-collision momentum is 200. Let's look at the post-collision momentum. So after the collision, they stick together. That's what happened in football. I mean, sometimes they bounce off, but a lot of times they stick together. So the post-collision momentum their mass is going to combine. So the total mass will be 175. And they're going to have a velocity. We don't know what that velocity is yet. That's what we're going to calculate. So from the law of momentum conservation, the pre-collision momentum, which is 200, equal to the post-collision momentum. So we know that 175 V times V is equal to 200. So when you solve for V, you get 1.14. 1.14. Okay, so the V is positive. So the both players are now going to move eastward because they stick together. They're going to move eastward with a velocity of 1.14. So you can see that the fullback lose momentum, and the lineman gains momentum because he actually changed his direction and now moves eastward. Okay, so this is important because if the fullback wants to score, he's gonna have to have more momentum than the lineman. Cannot gain his mass because his mass is fixed. He can increase his speed. By increasing his speed, he will gain more momentum and able to score. All right. So again, the law of momentum conservation is straightforward. The pre-collision momentum is equal to the post-collision momentum, and you can use this fact to calculate post-collision mass and velocity. So we're gonna stop here, and